Okay. Good afternoon, class. Here is Chih-Heng Lu from National University, the organizer of this SAR online course. Today I would like to invite to introduce you the today's lecturer, Professor Kuo-En Ching. She is a young professor in Taiwan and postgrad expert in Taiwan. She received his PhD degree from Department of Earth Science, National Sengkang University, maybe 10 years ago. I don't know. Currently, he serves as associate professor in Department of Geomatics, NCKU. So he is my college. His office just next to mine. And today, the lecture he would like to provide is the name is Crustal Deformation Monitoring using InSAR technique. So Professor Ching, the stage is yours.
Okay, so today I just want to talk about the crustal deformation monitoring. Basically, not just by InSAR techniques, and so the reason I will give you some. I would like to explain the reason later. And today I just want to focus on active fault and the earthquake. And maybe I will give you one slide to have a very brief, very simple concept about how do we monitor the volcano using InSAR. And actually, although we talk about InSAR, but I hope you could understand before we talk about this topic. Actually, we need to understand two terms first. The first one is the crustal deformation, and the second one is geodesy. Okay, so before we talk about the deformation, crustal deformation, I think we need to understand what is deformation. So if you check wiki or any other definition about the deformation, then it will show you the deformation is the displacement of a continuum body. So here we see we find another term, displacement. So what is displacement? I think maybe most of you think, okay, you understand what is the displacement, and there is the difference between the final and the initial position of a point. So here, please notice that when we talk about the displacement, even we talk about the deformation. So if we want to use any kind of methods to monitor one place, then we always need to identify a point. Okay, we need to detect the motion of a specific point. So this is the key. When we talk about the deformation or the monitoring of the crustal deformation, and I will emphasize this later, maybe in next slide. So then what is the crustal deformation? Okay, so then you will see here the definition just show us a change in the volume and the shape of the Earth's crust. So if we combine these two definitions, then we will note this point should be on the Earth's surface. So based on due to the Earth's surface was changed, then this point, the location change of this point will show us the surface deformation of the Earth. And then a very important key is, could we understand the mechanisms to cause this surface deformation? So just like here, sometimes I like to write something, okay? So here I would like to say crustal deformation. Crustal deformation is actually equal to surface deformation as mechanisms. So like this. But actually, we when we talk about crustal deformation, we not just talk about the surface deformation detected or monitored by the geodesy or geodetic techniques, but also we want to study the mechanisms. So if we come back to the topic today, InSAR as a technique, as one of geodetic techniques, it could help us to understand the surface deformation, especially related to the active faults or earthquakes or volcano. However, eventually we want to understand what kind of mechanisms from active faults, from earthquake, or from volcano to cause this surface deformation. So then, just like what we talked about earlier, so actually we have a serious geodetic techniques like GPS. Actually now many people like to say GNSS. So GPS is one of the technique of GNSS, and like VLBI, SLR, or like leveling, traverse, or InSAR. And actually, InSAR is the key is in this topic, in this lecture. LiDAR, photogrammetry, especially like the close range photogrammetry, and satellite image. So we have many kinds of techniques could help us identify the surface deformation. But I would like to say, usually I don't use LiDAR. The reason is very simple, just like what I mentioned earlier. So if we want to identify the crustal deformation or the surface deformation, then we always need to understand the motion of a specific point. Okay. However, the information provided by LiDAR is random point cloud. Okay, so the position is random. Okay, it is not a specific point, and that is very, very important for us to understand which the motion, the real motion of a specific point. So that's the reason now. Basically, we prefer to use GNSS leveling and the InSAR. So in general, to study the crustal deformation, especially for the study related to the active fault and earthquake and volcano. Okay, but you know, leveling is very, very expensive. So based on my understanding, in many countries, they usually use GPS and InSAR. Like three of my study areas, I mean international study areas. One is in Philippines, second one is Indonesia, and the third one is India, Himalaya in India. So most of crustal deformation study in those countries, they prefer use GNSS data. And you know, because the spatial resolution in those areas is not good enough. I mean, because the number of GNSS sites is not large enough. So in this case, we usually need to use InSAR to help us increase the spatial resolution of the surface deformation. Okay, because okay, like this, because the purpose of this lecture is to talk about the monitoring of the active fault and earthquake. So I just want to use this very simple example, a very simple example, to let you know what's the difference between surface deformation monitoring and the study of crustal deformation. Let me see. Okay, no one talk about this. Okay, so here, if we have two faults, okay, fault A and fault B over here, so this information maybe just gotten from a geological survey. Okay, and now if we want to build a road, and this roads will, or railroad or high-speed railroad, whatever. So eventually we know this road will pass through these two faults. So to maintain these roads, or we need to expect, we need to estimate the budget to maintain these roads in the future. Then we need to understand the damages caused by the activities of these two faults. So for this purpose, we have to understand the activities of these two faults. Then how do we note the activities of these two faults? A very, very simple way is to, I mean, for geodesy, okay, the easy way to identify or to detect the active faults, the activities of these two faults, just to install the GNSS station or use InSAR, okay, to detect the movement of these two faults. However, so whenever you install the GNSS sites or you use InSAR technique, you know, even we use InSAR technique, but you know, we will get a lot of the points, the velocity or displacement points from InSAR. So after you get this information, then how do you calculate or how do you identify the activities of these two faults? So please think about this before we talk about the following content. So what will you do? Okay, so in general, most people would like to install 4 GNSS sites or select the velocity from InSAR results across these two faults like this. So we will get velocity difference across these faults and another velocity grade this velocity difference across these faults. Then many people will say, oh, these two faults are all active faults because they are movement, they are moving, okay, because both sides of the velocities are different. So whatever you get the velocity from two GNSS sites, or from 2 pixels of the InSAR image. But if you have a velocity profile, so that means if you install a series of sites, or if you select the profile from the InSAR result, then in this case, you may get this kind of pattern. So like this. So the pattern will show you the velocity is low in this site and the high in another end site. Okay, so you will get this kind of arctangent pattern across these 2 faults. So you will see, based on this pattern, what we found we not only get the velocity difference across this fault, but also other places like here. So you could still get the velocity difference in this space, across this space, okay, and here too. So later I will show you why we make these decisions, or what kind of decision. So eventually, based on this study, based on this monitoring result, we know actually only the fault A is the active fault, and fault B is dead. Okay, it is not an active fault. Okay, so you know, I always like this example because in this example, it will show you that a very good concept that we could not just get the, when we understand the mechanisms of the faults, or the mechanisms of any sources, then we could not just how to say, calculate the difference using very seldom points. Okay, like this, 2 points. If you want to use 2 points to identify the activities of these faults, then you may be wrong. Okay, so the idea, just like this case, and this is a very, very classical introduction of the how do we use InSAR to detect the surface deformation. So this is the case of volcano, and after the eruption of the volcano, then we will see the subsidence, the surface subsidence of the volcano. So in this case, then you once you have the SAR satellite, okay. So based on Tsai's monitoring results, then you will get the phase difference due to the length subsidence. Okay, so you will get the interferogram like this. Okay, but here I just want to emphasize that once again, based on the surface deformation pattern, you will see not only the center of the volcano just goes down, but also other places, or the points at other places also go down in this case. But if we talk about the volcano, then actually what kind of reason to cause this subsidence in this case? So if we plot a very simple, if we draw a very simple figure like this, So we may have a volcano like that. Okay. So this is the volcano. And actually, the main mechanisms to control the surface deformation of this volcano is the magma chamber. So originally, we may have a magma chamber somewhere over here, okay, like this. So this is the magma chamber. Okay, and after the eruption of the volcano, then what we'll get? Oh, we will find the magma chamber will be the size of magma chamber will be decreased like this. So after eruption, will look like this. Okay, and then in this case, then we will see the once again the volcano like this. You will goes down. However, something look like this. Okay, so then this figure. Okay, we will get the subsidence. Okay, at this volcano. So this case just show us, although the mechanisms or the source just like a point, okay, like point, okay, just image that it is a point. But the surface the change of surface deformation pattern, just like a phase or an interface. Okay, so it is an aerial change. Okay, so it doesn't mean if this part the size of magma chamber decrease, it just cause the subsidence at this point. So it is wrong. Okay. So if we look at another case study, so there is the length subsidence, and here I just want to use the length subsidence to give you the same concept. So the deformation is the surface deformation is it is not a point. So like this. So this is the case of length subsidence in central Taiwan. So here you will see the pattern of the length subsidence, just like a circle, a series of circle. Okay, so that means if we want to detect the length subsidence, then we want to identify the series circles, then the center of the circle will be the center of length subsidence. Okay, so although it is a point, however, it calls the length subsidence in an area, in a range, in a region. Okay, so in this case, once we have a road or a railroad pass through this area, then if we want to identify the effects of the land subsidence on this railroad, then we could not just identify the vertical deformation along the railroad. We also need to understand the deformation, the surface deformation in other area, because always keep in mind, the reason we want to monitor the surface deformation just because we want to predict or we want to estimate the disasters of the caused by the faults or land subsidence or any other geological disaster. Okay, so then if we come back to talk about the active faults and earthquake, so this is the map, the InSAR results in southwestern Taiwan. So if you know the Kaohsiung city in Taiwan, it is the second largest or third largest, it depends. Okay, in Taiwan, and of course it is the largest city in southern Taiwan, and it is my hometown. Okay, so here just shows the InSAR velocity, left-side velocity. It is the ascending result in southwestern Taiwan. Then how could we get the information related to the active faults based on this figure? Of course, here you could see some dashed lines. So those dashed lines are the proposed active faults in this area. However, how do we know the proposed lines are correct? Okay, or could we get any information about the activities of these fault tracks based on this figure? So again, like the case study here, we could not just use 2 points across the fault to identify the activities of the fault. Okay, so now I just want to show you how do we understand or how do we analyze the velocity field, surface velocity field, to understand the activities of the faults. And why do we want to focus on active faults and the earthquake? Okay, and actually there is why the question, why do we study earthquakes? Just because, and I always like, I like the movie San Andreas so much. Because in this, although this movie is not so, how to say, not so realistic, but it could show us a very, it could give us a many good idea how to teach. Okay, so we note serious cracks may occur on the ground. Okay, and those cracks like this could be related to the faults. So we always know earthquake occurs on a fault due to the slip on the fault. Okay, so basically the reason we study the active faults just because we want to estimate the earthquake potential or we want to predict the next earthquake. And this earthquake, the occurrence of the earthquake not just cause the damages of the buildings or the ground or like this is the road, but also we may get the tsunami okay, then the tsunami may cause another very large damages, okay, following the earthquake. However, this figure is wrong, okay, because the active faults in this region is inland but not offshore, okay. But however, this is movie. Okay, so before we talk about the active faults, just we always need to understand the purpose of why we want to monitor the surface deformation related to the active faults using InSAR or other geodetic techniques. The reason is simple, just like what I said. Earthquake is caused by the slip on the fault. Okay, so we want to we want to understand. We want to estimate the earthquake potential or even predict the next earthquake based on the study of active faults using the geodetic techniques, including InSAR. So to achieve our purpose, we need to understand the how do we evaluate the probability of the earthquake, or what's the concept of the earthquake prediction. Then we will know what kind of information do we need for the active fault study. Then we will understand how could we extract the information from InSAR to help us answer the questions related to the active fault. Okay, so every time when I talk about the earthquake, I always like to use this tank model. Okay, so here you could see this is the water tank. So please image that. We always need to recharge the water from somewhere. Okay, we want to put some more and more water into the tank. And of course, we always need to use the water, so we always could get the water from this tank. So please image that if we assumed the water tank as fault, and then the water will be the energy. Okay, so the energy occurring the earthquake. So if we refilling the water, then it means the energy accumulation on the fault, and the energy release will means the earthquake occurred. Okay, so the earthquake may be just like a reservoir, water reservoir, and if the dam crash, or if we want to release the water from the dam like this, then you will see a lot of energy will be released in a very, very short time, like in few minutes or a few seconds. Okay, so that is the earthquake. And based on this figure, or based on this slide, so that means if we want to understand how to if we want to predict the earthquake, or if we want to estimate the earthquake potential, then we always need to understand several parameters, like what's the size of the water tank. So that means what's the size of the fault, and what does that mean? So that means once the energy released from this tank in a few moments, then the size of the water tank or the size of the fault will be equal to the maximum magnitude of the earthquake. Okay, so this size of the water tank will give us the information of the possible maximum magnitude of the earthquake. And then we also need to estimate how much energy already released from this tank. Okay, and then we need to estimate how much energy accumulation rate in this region for this tank. Okay, so based on this balance calculation, then we may have some guess or have some probability estimation for the next earthquake. Okay. So based on in this case, then usually the study of energy release is the earthquake. So based on the earthquake study, then we could understand how much energy released on this fault. And we also call it co-seismic deformation study. And if we want to study how much energy accumulation on the faults, then there is the interseismic deformation study. So why is the co-seismic and interseismic? So here is a very simple idea. So if this is the time, so this is time, and usually is years. So that this is the time. Okay, if we know once the earthquake occurred over here, and here, so they are first earthquake and the second earthquake. Okay, so we usually set the co-seismic period. So we usually say, oh, okay, here is the co-seismic period. So the deformation related to the earthquake, we also call it as co-seismic deformation. Okay, and here I just give you a very, very simple concept. So if we have another like this, okay, so if we notice that between earthquake, there is a very a long time. Okay, so we call it interseismic period. And its related deformation is interseismic deformation. So usually we could understand the energy accumulation, energy released based on the co-seismic deformation. And we like to study the energy accumulation that's based on the interseismic deformation study. So those are the general idea. Okay, so this is the general study related to the earthquake, and so here just like what you know, when we talk about the co-seismic, this is the surface deformation or crustal deformation. So that means once we get the, if we want to study the co-seismic or interseismic crustal deformation, then InSAR will be one important techniques to provide us some information related to the energy release or energy accumulation. So what is that? So how do we use them to study the energy accumulation or release? So first, we just look at the case related to the earthquake, the energy release part. So like here, this is the case study in Taiwan. So the earthquake occurred over here, and based on the GNSS data or GPS data, we could calculate the displacement caused by the movement of the faults during the earthquake. So we call it the co-seismic displacement. And here is the horizontal pattern, and this is the vertical pattern. So once again, although the movements, the strip on the fault is within a very small size of area, it could be somewhere over here, but it could cause large scale surface deformation. So you could see the the area of co-seismic displacement fields of this earthquake may covered almost half of Taiwan. So again, when we study the surface deformation or crustal deformation, we always need to monitor the surface deformation in a large area. Okay. However, how do we know? We always emphasize that the surface deformation, this surface deformation is caused by the movement of the fault. So that means once we note the surface deformation, then that's it possible for us to understand the movement of the fault. Okay, the movement of the fault. Because once we understand the movements of the fault, then we could estimate how much energy released on the fault during this earthquake. Okay, so once again, the idea is because we want to achieve the purpose of earthquake potential estimate or earthquake prediction. So we need to understand how much energy released or how much energy accumulated on the fault. Okay, so to understand or to estimate how much energy released on the fault, then we need to evaluate how much slip or what's the slip distribution on the faults during the earthquake. And because the movement of the faults may cause the surface deformation. So once we detect the surface deformation during the earthquake using geodetic techniques like Yunung Nina leveling or InSAR, then we could evaluate the slip distribution on the faults during the earthquake. Then we could calculate the energy release on the fault during the earthquake. So that is the idea. Okay, but how do we know the what kind of faults cause this surface deformation? So here I'd like to show you several cases. Okay, it will give you some simple idea about how do we know which fault, how do we know, how do we use the surface deformation to understand the mechanisms associated with the fault. So here I give you one sample. It shows here the white rectangle is the surface projection of the fault. If we look at this profile, then you will see the fault. The fault is over here. Okay, so this is depth and distance. So here is the fault. And here I show you two faults. The first kind of fault is that the upper depths of the upper bounds of the faults doesn't reach the surface like this. Okay, so here you could see the upper edge of the fault plane is at around 2 or 3 kilometers below the surface. And this case just show us the fault rupture to the surface. So here you could see the tip of the faults reach the surface, reach the ground surface, so at 0. And then all of them are low deep angle thrust faults. So deep angle is 30 degrees. So please keep in mind the deep angle. And this is the reverse fault. But in this case, then we could see, although both of them are reverse faults, however, the magnitude, and the strip are the same on these two cases. However, we could see the surface displacement pattern is similar but different. Okay, similar is that we could see the direction of the surface deformation. The arrows are the horizontal displacement, and the color map just shows the vertical displacement. So here we could see the horizontal displacement and shows the similar pattern, but the magnitude of this case is higher. Once again, I assume all of you already know the line of the relationship between line of sight and the 3D displacement. Okay, so that means once we get the 3-dimensional displacement field or deformation fields, then we could always project the 3-dimensional displacement or velocity into the line of sight to get the line of sight velocity or line of sight displacement. And that is the results from InSAR. Okay. However, usually it is not easy to understand the pattern of line of sight deformation. So we usually like to to learn the three-dimensional deformation caused by the faults in the beginning. And then we could check what kind of pattern look like from the InSAR data. Okay, so this is the horizontal displacement and vertical displacement caused by the low angle fault, low angle reverse fault. However, if it is the high angle reverse fault like this, the dip angle is around 50 degrees. Okay, then you will see the pattern of the horizontal displacement are different. The vectors here in these sides are smaller, but the vectors over here is high. Okay, so the idea is the pattern are different. So in the low angle thrust faults, the vectors here is larger than the vectors here, even this case. Okay. However, for the high angle reverse faults, the patterns are different. So many people told me, if we know it is a reverse fault or thrust faults, then we could always get the based on the monitoring results, we could always understand what kind of faults. I mean, they always think it is very simple to understand what kind of faults based on the InSAR result or based on the geodetic data. However, they don't understand the pattern may be different or quite different. Even all of them are reverse fault. The only one difference is the dip angle. Okay? So that means before we study or before we monitor the surface deformation, we always need to understand what kind of mechanisms or what kind of source you want to detect to cause this surface deformation. Okay. Or once you get the pattern of the surface deformation, you always need to understand that what kind of mechanisms may cause what kind of surface deformation. And like this. And this is the surface deformation, surface displacement caused by the normal fault. Okay, so because this is the case of the earthquake, so if you learned, you know, every time when you learn geologists, then geologists will tell you what is the normal fault. So they will say, oh, this is the normal fault. Oh. So they will tell you this is the normal fault because here is the hanging wall and here is the full wall. So the hanging wall goes down relative to the full wall, then it is normal fault. Then based on this figure, you will expect the co-seismic displacement will look like this. Everything on the normal fault may goes down like this. Okay, and the pattern of horizontal displacement may look like this. However, here just tell you, yes, the normal form means everything on the hand wall will be go down, but the magnitude is different. Okay, the largest one is located at the location very close to the faults, and it will decrease away from the fault. How however, if we look at this horizontal displacement, then we will see not only the extension here, but also we could see the we could get the in this case is the right lateral strike slip component and the left lateral strike slip component at these two ends of the fault. So the pattern is always not so simple like this. Okay, this is the conceptual model only. Okay, and this is the real world. So that means once you want to study the crustal deformation related to the active faults and the earthquake, then you always need to understand what kind of surface deformation pattern caused by the fault during the coseismic period or the interseismic period. Okay, and see, even for the normal fault, so this is normal fault, and this is the surface displacement inferred from the normal fault, and their dip angle are the same. But in this case, the faults doesn't reach the surface. And in this case, the faults reach the surface, and you will see the pattern are totally different. Okay, so that means we always need to understand the pattern of surface deformation first. And this is the strike slip faults. This is the left lateral strike slip faults when the fault planes doesn't reach the surface. And once it reaches the surface, then the pattern will look like this. Okay, so the case of strike slip fault is much easier. Okay, so but how do we estimate the energy released by the released on the fault based on the surface deformation pattern? Okay, so usually we like to use the dislocation model. It is the most simple model for us to understand the surface deformation related to the fault. Okay, here I just see a questions. He asks, what different phase to displacement snap and vertical displacement formula used in band math? Okay. Actually, I want to say that. Okay. Maybe I need to emphasize one idea is I just try to respond to your questions. When we talk about the surface deformation like this, okay, whatever a volcano or any kind of mechanism, then we always have the displacements in 3-dimensional. So east and north for horizontal and the vertical displacement. So we have 3-dimensional displacement. Okay. And then, so that means what's wrong? Okay. we have 3D displacement. So means east, north, and vertical component. Okay, and then because we note the InSAR or SAR is line of sight. So because of the design of SAR satellites, so we could always get if I assume this is satellite, okay. So actually what we get, the information what we get from this satellite, just one line, this line. And we call it line of sight. Okay, I guess that is what you learned in previous course. Okay, so because now side just one component. So here we have three component, 1, 2, 3. We have three component for three-dimensional displacement. But the line of sight displacement is one component. So it is one component. So we always need a projection, something like this. We need to project the three-dimensional displacement into line of sight displacement. I know maybe you already learned some techniques to try to convert line of sight into maybe three-dimensional displacement or two-dimensional displacement. So you may learn if we have ascending and descending line of sight displacement in the same area, then we could calculate based on the projection. So we could calculate the vertical. So there is the U component. So vertical displacement and the east component. So east displacement. However, this convergent, this how to say, this translation or projection may lose some information. So the better way for us to understand is to project the three-dimensional displacement into line of sight displacement. Okay. However, how do we get the line of sight displacement? We usually get the what? Interferometry. I always has the problems about spelling. Okay, so actually we get the line of sight displacement based on the unwrapping from interferogram from phase. Okay, so there is their relationship Let me check once again. Okay, so actually you could have a lot of different software to unwrap the interferogram to recalculate the phase into displacement. Okay, because different fringes, I mean different SAR may show you different bands. Okay, it provides different wavelengths. So based on different wavelengths, then you could calculate the line of sight. Okay, and now the key is not about the line of sight displacement. When we talk about the monitoring, okay, when we talk about the monitoring, the key is surface deformation itself. So always keep in mind the surface deformation is three-dimensional displacement, is three-dimensional deformation. Okay, so the line of sight displacements only provide us two-dimensional information, and basically, or if we only have one, how to say, if we have ascending or descending only, then we have one component information. Okay, so the questions or the problem will be, how could we identify the mechanisms or how could we study the crustal deformation using InSAR result? Okay, but once again, just like what I said in the beginning, the purpose of crustal deformation study is to understand the mechanisms. Okay, so like if we use the faults, the faults or earthquake study as an example, we always want to predict the earthquake or estimate the earthquake potential. So that is our purpose, final purpose. Then how could we use the InSAR result to help us study the earthquake potential estimate or the earthquake prediction? Okay, but always keep in mind, InSAR or line of sight displacement is just provide just one of the geodetic techniques, and it has all kind of geodetic techniques have limitation, have their limitation. So we always need to understand their limitation, then we could understand how to apply those techniques to our study. Okay, so if we want to understand the earthquake potential or earthquake prediction, then we need to we want to use the geodetic data, the surface deformation pattern, to evaluate the slip on the fault. Okay, then we could study the earthquake. So we have a series of geodetic techniques, and InSAR is one of them, but very, very powerful. Okay, so in this case, you will know once you have learned how to convert the phase into line of sight displacement, then that is what we will use in this crustal deformation study and the following applications. Okay, I don't know, do I really answer your questions? So if yes, please let me know. If you still have further questions, please just also let me know. Okay, thank you. Okay, and then we just come back to this dislocation model. So this part is very important. How do we get the information from the surface deformation to the mechanisms? We always need the model, numerical model. So a numerical model is the key. To connect the surface deformation and the mechanisms like this. So if we want to understand how the volume change of the magma chamber to control or to dominate the surface deformation, then we need the numerical model to show us the relationship between the surface deformation and the volume change of the magma chamber. And same idea. If we want to know how much energy released on the fault during the earthquake, based on the surface deformation during the earthquake, then we always need a numerical model. So this numerical model associated with the fault is a dislocation model. Okay, so based on this dislocation theory, based on this dislocation model, so after we construct the fault plane, and if we know the surface deformation, so this surface deformation results may come from InSAR or GNSS, then we could get the slip on the fault plane. And then once we get the slip on the fault plane, then we could estimate how much energy released in an earthquake. So that is the simple idea. And then here I use the 2016 Meinong earthquake in southwestern Taiwan as an example. So first, once the earthquake occurs, then we always could calculate the co-seismic displacement of the earthquake. So here shows the horizontal displacement and here shows the vertical displacement. And in this case, you could see actually the data points is not much. Okay, not so many. Okay, and we still have a lot of space without data. Okay. In addition, we also get some weird pattern like this. Okay, like this one or this two. Okay, why I say it is weird? Because usually, the largest displacement may occur at the source area, and the pattern, the direction of the movement is systematic, like this. If it goes in this direction, southwest direction, then everything just go in this direction. And if we turn to northwest, then you will see the pattern will change gradually from southwest to northwest. However, for this point, it just changed suddenly the direction. So and it is so weird. Okay, it doesn't look like it's caused by the earthquake. So, and actually, once we go to the site, so the site is over here, then we will see, oh, so this site is on the dam of a water reservoir. However, during the earthquake, the dam was the damage just occurred on this dam. So it caused sudden displacement. Okay, so the pattern here it shows 6 millimeter displacement. Okay, it is the artificial displacement. Okay, so if we use the GNSS or GPS data, then we usually encounter this kind of problem. Okay, because we don't know unless we go to the fields or we don't know what happens in this site. Okay, however, if we have InSAR results, then so this is the InSAR result. This is the results from ALOS 2, and this is the result from Sentinel-1A. Okay, and based on the D-InSAR calculation, I guess all of you already know how to calculate the D-InSAR, or the theory, the concept of D-InSAR. Then we could get this two pattern. So here you will see we have because this result is line of sight displacement. So first we could know the displacement is high in this area, and the earthquake just occurred. Where is the earthquake? Oh, earthquake is here. So earthquake is somewhere over here, but the large displacement is over here. And you know, once the earthquake occurs, and when people see this pattern, then many people just wonder why the large co-seismic displacement just occurred in this site. But once we get the InSAR result, we just confirm that, oh yes, the GPS data is correct, and the main co-seismic displacement area is west of the epicenter. Okay, and we have 1, 2, and maybe 3 large displacement area. However, because this is the line of sight displacement, so it may be contributed by the horizontal displacement, that is eastward displacement or vertical displacement. Okay, so here usually we like to do some comparison. Okay, so in this case, if we overlap the InSAR result and the horizontal displacement, and we overlap the vertical displacement result and the InSAR result, then of course here we will see. So basically, we could get the we understand that the high line of sight displacement during this earthquake is mainly dominated by the vertical displacement. Okay, and one more important thing is you could see based on this GPS data, then we know, okay, the general pattern just look like this. Okay, however, and like this. So here it has a high a vertical uplift. Okay, uplift here, uplift here, uplift here. So based on the pattern, based on this pattern, then I will image that, I will guess that the all of this area is uplift, but based on the InSAR results, then we found what's in this area, this blue region, it is subsidence during the earthquake. Okay, and subsidence once again over here. So it is very, very important for us once the co-seismic displacement pattern is complicated, then only the InSAR data could give us a very good information related to the earthquake, to the co-seismic displacement, because it has a high spatial resolution. But once again, please keep in mind, because this area is the plain area, coastal plain. So, and even here is the metropolitan area. So we could always get a good results from InSAR. However, like the area over here, it is they are hills, and they are hills. So we could not get the signals in those regions. Okay. So one important issue is that even in SAR, we still could not get a very good information from the vegetation region, okay, because we could not get good signals unless we have others to the L-band result. So L-band result usually could get a much better information in the mountain area, okay? And then just like this. So here I just show you the comparison of GPS, the horizontal and the vertical displacement. Actually, we also have the comparison of InSAR result, okay? But whatever, because here I just want to show you the results of surface displacement and co-seismic slip on the fault. So the warm color here shows the slip distribution of the fault, and the other arrows are the surface displacement. So here you will see, based on the modeling result, so just we use this dislocation model. Okay, then we could match the calculation and observation over here. Then once the model could predict the observation, then we could understand the distribution of the slip on the fault. And once again, once we know the slip distribution on the fault, then based on the information of slip and the rupture area, fault area, then we could calculate the energy released on the fault. And based on this result, we also know that first, we know the fault is over here. Okay, this is the projection of the fault plane, and here is the location of the fault plane along the cross section. So it is a very low dip angle fault plane. And the main rupture area, so there is the main energy release area is over here, not on the location of the epicenter. Okay, just by the location of the epicenter. Okay, and then we know in the future, the same area over here will release the energy and cause the earthquake once again, maybe several hundreds or several thousand years later. Okay, so that is what we learned. Of course, just like what I said, we could calculate the energy release. So based on other methods, we could even calculate the time variance energy released on the fault plane. Okay, so this is what we learn from the earthquake. Okay, so again, because we want to predict the earthquake or estimate the earthquake potential, so we not only need to understand the size of the water tank, so actually that's the size of the fault, and just like this. So based on this fault model, we also know the size of the rupture area on the fault. Okay, so it will show us the magnitude of the earthquake. So once an earthquake occurs, then we could check, we could get the precise information of the faults in the deep of the earth, in the earth's interior. Okay, and then we could also estimate the energy released during the earthquake. Okay, based on the surface deformation pattern like this InSAR. Okay, so that means based on this dislocation model, we could also generate the line of sight displacement. So it is very simple, just like what I said here. So once we have the three-dimensional displacement, then we could project it into line of sight components, then we could get the line of sight displacement. And this line of sight displacement is generated by the unwrapping of the interferogram from InSAR result. Okay. However, we also encounter other problem is if the quality of the tank is not good enough, then it means some leakage may occur in this water tank. So actually, there is the case of creeping faults. So creeping faults usually means the faults which energy keeps being released on the fault aseismically. So aseismically means the movement of the fault without earthquake. Okay, so that means the slip or the slip rate of the fault is usually very, very slow. So here, oh my goodness, sorry, because I gathered several slides together. Okay, so some of the slides in Chinese, but however, I will explain it in English. Okay, so here I just want to give you another example about the creeping fault detection using the geodetic data, and here you will see InSAR will play a very important role in the detection of the creeping fault. Okay, so here is the southwestern Taiwan once again. Just basically south of the source area of the 2016 Meinong earthquake. So if we go back to see, okay, here. So you will see, could you see this hill? And this is the harbor. So this is the Kaohsiung harbor, and there is the largest harbor in Taiwan. Okay, so please remember these two pattern feature. So where we are here, oh sorry, okay. another feature is this harbor. So this harbor is for military usage. Okay, this one. So let's see. Here is the harbor for the military, for Navy, Taiwan Navy, and this is the hill. Okay, so this area, this study area, just south of the earthquake. So the earthquake should be somewhere over here, and the main rupture area just north of this region. Okay, so why do we want to understand the surface deformation in this region? Just because of this one. So here you could see a polygon here. Then this polygon just indicates the science park in Taiwan. So it is a high-tech factory field in Taiwan, and this is a new one. However, in this map, you could see some dashed line. So actually, this dashed line just show us the proposed active fault in this region. So we will see there is a fault just passed through this science park, and that is very dangerous because if most of the factory are high-tech factory in this science park, but we have one active fault just passed through this park, this science park, then it means the whole factories in these sites will suffer the how to say, the damages caused by the earthquake. Yeah, and because the fault just passed through it directly. Okay, so here just show you the plans, some plans of the factories in this region. Okay, so oh, by the way, not only the fault but also mud volcano. So there are one mud volcano just located in this science park. If you comes from the Indonesia, then maybe you know a very famous mud volcano, but I don't remember the name in Bahasa Indonesia. But I just know the English name is Lucy mud volcano in East Java, just south of the Surabaya. Okay, and actually in southwestern Taiwan, we also have a lot of mud volcanoes, and one of them just inside the science park. So now the problem is, could we understand the or could we realize the activities of those faults based on the geodetic data? And could we use InSAR results to recognize the type of faults or the locations of faults? And this is basically what we want to understand. And why we want to use the geodetic data to understand these questions. Just because if we go to these fields, then we will see this is the mud volcano. So over here, the mud volcano is here. And then we will see all of the area, okay, maybe not all, more than 90% of the areas or fields are formed, okay, in this region. So almost no buildings, and but however, nothing else, okay, just a vegetarian, vegetation. So that means you know, if we want to identify the creeping fault, using the methods of geologists, then we usually need the buildings or any artificial constructions in the area. And once the faults pass through the constructions or pass through the buildings, then the cracks on the building will record the displacement of the faults, and we will know it is the creeping fault. So this is the general idea. However, in these areas, everything is field, everything is vegetation or soil. So please image that if the rate of the slip rate of the fault is around 2 centimeters per year. So that means the faults will move 2 centimeters using 1 year. Okay, and 2 centimeters per year is extremely high slip rate. Okay, in the world, okay, 2 centimeters per year. However, because Taiwan has a lot of rainfall, so once the rainfall occurs in this region, then you will see the displacements, the cracks caused by these 2 centimeter movements will be destroyed by the rainfall, heavy rainfall. Yeah, okay. So that means we almost have no idea how to find out the evidence from the geology in the field, okay? And if the fault is the creeping fault, then that means the fault moved without earthquake. So that means seismologists could not tell us anything about the creeping fault in this region based on the seismic data. So the way we want to understand the surface deformation, or if we want to recognize the type of fault in this region, then geodetic data is the only way so far, or the only best way so far. So here shows the horizontal velocity and vertical velocity in this region. So horizontal velocity just derived from the GNSS data, and the vertical velocity derived from the continuous GNSS data and the precise leveling data. However, unfortunately, if we look at the sites of the science park, then what happens? No observations occurred. No observations is in this site, okay, from the Central Geological Survey data, okay. However, based on this horizontal velocity pattern, we still could get a velocity just increase from north to south, okay. However, we still have no idea whether the creeping fault passed through this science park. And based on the vertical velocity, we get almost no systematic pattern. So in this case, InSAR will be important. Okay, so InSAR results. So in this case, you could see InSAR result will provide us a good spatial resolution results, and but once again, you could see once the sites located at the hill area or mountain area, then we won't get good results in this site. And even in the science park area, we still get few data. Why? Just because because of this. Now, most of area has vegetation, so that means the correlation, the coefficient, correlation coefficient. Somebody forgot that. Okay, the consistency is not coherence. Okay, the coherence is still not good enough in the science park area. However, even though we still could get some important information inside the science park, and we could see here, you could see, oh, maybe I could enlarge. See, could you see a very significant velocity, color change, color difference across this line? Okay, across this line here and here. So this is the results from ascending, and this is the result from descending. So here you could see we could get some information from the ascending, but from descending, actually we could not detect the very clear velocity displacement, velocity great difference. Okay, so so they also show you, it also show you the limitation of the InSAR. So once again, ascending and the descending are very important. So if you have only one track, then you may miss some information. Okay, and okay, so here, how do we identify the creeping fault? And here just show you one case, one concept. So here is the modeling results. So if we assumed the faults reach to the surface, so once the faults reach to the surface, so that means the locking depth is 0. If the faults, if the upper bound of upper edge of the fault is 5 kilometers, then you will see the velocity gradient is lower than this one. And with the increase of the bottom, with the increase of the top of the fault, okay, then you will see the velocity gradient just decrease. Okay, so that means velocity gradient is the key. So if the fault is the creeping fault, then we will see a very clear velocity difference across the fault. And actually, that's the way, and that's the reason we need InSAR, because usually the density of the GPS network or other traditional network, a geodetic network, is not high. Especially like this case, because we don't know the fault before. So that means it is impossible for us to install a very, very dense network across this fault. However, in this case, InSAR could give us another solution, because if the area is good enough, so that means less vegetation, less and more buildings, then we could get good spatial resolution of surface deformation. And then in this case, then we could get a very dense velocity data across the faults and very, very close to the faults. Okay. However, just like what I told you earlier, because InSAR data provide us line of sight velocity or line of sight displacement, but usually we need the three-dimensional velocity fields, like horizontal and the vertical velocity, like this. So we usually like horizontal or vertical velocity. So in this case, we like to use a way, at least one way. So there is the velocity inversion. So this velocity inversion could help us combine the horizontal velocity, vertical velocity, and the line of sight displacement, line of sight velocity from InSAR. So here are the results. We use this velocity inversion methods. Then we could combine all of these results, and we could get a good horizontal and vertical velocity. Here, I also do some uncertainty estimation. Yeah, because I want to evaluate the reliability of this result. And then here you could see it. Here shows the value of the uncertainty in east, north, and the vertical components. And then you will see it in general, the uncertainty of east component and the vertical component are around 1 to 2 millimeter per year. So that means the reliability of this velocity inversion is high. However, for the north component, then you will see the highest uncertainty may reach 8 millimeter per year. Okay, so it is very, very high. And you know, I guess maybe now you already guess the reason. Okay, the reason is simple because InSAR is line of sight velocity, so it means the most information in north component. Okay, it could get the information from east and the vertical component. So that's the reason we could get a good reliability in east and the vertical component, but poor resolution or poor reliability in north component. Okay, so that is the way we learn from InSAR. So based on this result, then we could try to understand which segment of fault is creeping and which segment of fault has potential to generate the earthquake. However, here, do you notice that one thing in the InSAR result, we do see the creeping, but in this how to say modeling results, we don't see a clear velocity difference. So that means actually we need to modify the code. Okay, so modifies the methods. So in this case, then you will see the different results. So in these results, we not only contains the InSAR and the GNSS, continuous GNSS data, but also we consider the creeping effect. So here you will see the horizontal velocity is a little bit, the pattern is a little bit different from here to here and from here to here. And see, sorry, here. And we could get a very clear velocity change from here to here. Okay, just like what I show you here. So once the fault is creeping, then we could get a very clear velocity difference. And then, of course, the matching, the data matching here is much better. So eventually, based on this result, then we could map the faults much more clearly, and we could identify which segments, like here, eventually we know this segment of fault is creeping, and we know the type of fault based on this data. So this is the case of interseismic deformation, okay, because all of these results are gathered, are collected during the how to say, between two earthquake. Okay, so I think this is the final slides. I hope in these lectures I just give you one give you the concept of the the relationship but between surface deformation and the mechanisms like the faults, the slip on the fault. And I also show you the concept of the surface deformation and the geodetic data or geodetic techniques. So InSAR is really very important to increase the spatial resolution of the surface deformation, especially for the creeping fault identification. Okay. However, the GNSS data is still very important for us to constrain the InSAR result, just like this test. So based on this test, we could know if we don't have a good constraint from the GNSS, then we may misunderstand the information provided by InSAR. Okay, thank you. So you have any other questions? And here you have I thought one question, QGIS. Yes, sure, of course. QGIS is a very good platform for us to demonstrate the results, okay, to get the visualization. So sure, no problem. However, just visualization for me. Yeah, because you could not use QGIS to really understand the mechanisms. You could not use QGIS to analyze the velocity. Yeah. So do you have any other questions?
Good evening, Professor. Can you hear me?
Oh, okay. Now, yeah, I hear you.
Oh, okay. Yeah. So I have one question is because just like you said, the creeping faults they are move very slow, so about 1 centimeter or 2 centimeter per year. So my question is because in theory, this kind of creeping faults, their movement is happen on a rock layer, but it won't happen on the soil layer. And when a rock layer, when its faults they are used very slowly to move, so the soil that cover this rock, because the soil is one of the flexible component, it maybe has some relative movement between the soil and soil, and it might be covered the real movement rates of this faults. So will this kind of effect to cover the real movement rates of the faults because the soil?
Yes, very, very good questions. So actually, we do detect this kind of information. So yeah, you are right. So that's the reason GPS, GNSS, or some traditional techniques is very important, because if the benchmark, because for GNSS or for leveling, we usually like to survey, we like to measure the position of the benchmark. So once the benchmark could stick, how to say, if the depth of the benchmark could fix in the rock, okay, just penetrates the soil layer. So in this case, then we could detect the true movements of the faults. However, if we use InSAR, then we will see InSAR could help us identify the just surface deformation. So we may just detect the movement of the soil, then you will get less information, less velocity or less surface motion. Yeah. So in this case, then once you have the InSAR results, then maybe it is better for you to understand whether your results comes from the reflection of the buildings or from some rocks. So just from rocks, then maybe it is not the true signal, especially from the soil. Okay, and actually we found the problem in the field. Yeah, so very good question.
So if we use the ground penetrating radar, can we get the better accuracy, ground-based or airborne? Because maybe our ground penetrating radar, they cannot directly to see the rock, but they can see the different depth inside the soil particle. So it can be used a different depth inside the soil particle, their relative movement, and to do the one roughly data model and roughly to calculate what is the real movement rates of that rock plates. So is that possible?
I don't know. I never test. So even I don't know how this the how to say maybe you could do some test. Yeah, but I don't know. I need to. Nobody think about that before. Yeah.
Oh, okay, thank you.
Yeah. Southern slope, which ascending or descending will provide good. Southern slope. Maybe. Yeah, maybe. Southern yeah. Wait a moment. No, sorry, because it depends. If you especially in the mountain area, in the mountain region. So if you want to talk about the landslide, you usually it is the landslide issue. So you still miss the information in the slope, in this kind southern aspect slope. Okay. However, if you want to talk about the fault, maybe you have a chance to get the information from ascending result, ascending image. So there is my my response. Okay. So any other questions? Oh, a shift. A shift between GNSS and the InSAR. So it depends on what kind of shift do you encounter. So maybe in this case, I would suggest you to have a discussion with other lecturers. But based on my experience, if your InSAR result is if you could solve the InSAR result very carefully and very reliably, and like the case, like my case, like this case, okay. In this case, I compare the GNSS line of sight and the InSAR line of sight velocity, and then I found they are almost the same. So that means I don't need to do any correction. I don't need to do correct the shift because they could match each other very well. Okay, but there is the case you deal with the InSAR data very good and the GNSS data very good, and you could make sure their reference points are the same, because usually people doesn't care about the reference frame issue. Okay, so they always get some shift. Yeah. Okay, so there is the idea. Okay, so I guess because time is up, so if you don't have any further questions, I think we just end off here. And if you have any further questions, just email me. Okay, so here in the beginning. Okay, so here you could see my email address. Okay, so thank you, everyone. So
thank you, Professor Jin.
Thank you.
Thank you for your nice talk.
Okay. Thank you. Okay, bye-bye.
Bye bye.